So we're looking at the sitemap device and its overview screen that is obtained at the end of all the measurements. The overview screen at the top right corner has the patient's demographic details. It importantly has the subjective refraction mentioned there, which is collected prior to the sitemap assessment. Beneath that is the date of the examination, which is quite obvious, and then there are a series of measurements that have been taken. For each of those measurements, one has the pupil diameter, the myopic sphere correction, the cylinder correction, the axis, and the spherical equivalent. The spherical equivalent has to be within half a diopter of the subjective spherical equivalent. If it's more than that, then you get a tick that says it's not green. If it's within that half a diopter, it's a green tick. So the QS, the quality tick mark that you're getting, it looks at a variety of things. It looks at the pupil size being adequate. So in this particular measurement, sometimes the pupil is going below 6 mils. It's sitting at 5.67, 5.68. In this particular case, the patient has a SIL of 0.75, and we are reading about even as high as 0.97. It's somewhere between, it's around 0.9 plus minus 0.5, and the axis is sitting at 85, whereas the measured axis was sitting at 80. There's a 5-degree difference. Generally, if we are to go back, take the patient back, you will find 5 degrees is not very large, but even when it is a bigger difference, that the patient's responses will be faster at the refraction that the wavefront data is providing. To the right of it is the infrared image of the eye, and then is this image, which is quite relevant to look at from a qualitative perspective. This is showing the beams of light that are passing through the system. And whenever a beam of light does not match where its expected location is, then you know that beam of light has been deviated. So for each of these beams of light, you can calculate the deviation, and that's how the wavefront data is being utilized. And you can basically create a heat map of the higher order aberrations, and which is what is presented to the right side. You can choose other views, but this gives you a rough idea of where the higher order aberrations are spreading in a topographical way. That top row is entirely Hartmann-Shack wavefront aberrometer based data. The next one is fairly straightforward. This row is about axial length. And here you can see we've only taken 2 measurements. Most of the patients are phakic, obviously, and they're young, so they don't have a cataract. So getting their phakic axial length, it does not require multiple measurements. You are getting exact overlap. And so this is a fairly simple and straightforward measurement to take, and it's quite intuitive. Then comes the topography data. The topography data, the tomography data is presented in a very simplified format. It's showing you the Scheimpflug image. It's showing you this image, which is the infrared image which you're going to use for image registration. The most important bit on this section is the image registration. You've got good quality images for registration during surgery. If this is too big or too small, then it becomes difficult for registration during the surgery. This data is a sagittal map, the axial/sagittal map. And if you need to look at it in detail, which you do, you want to see the tomography data, you would go to the display setting and find your standard 4-map refractive data. And you can find your Bellin-Ambrosio curve for looking for ectasia or suspect keratoconus in this case. One of the other interesting features of this presentation, this overview screen, is this wavefront detail. The wavefront detail gives you the wavefront measurements roughly for that. It breaks down the wavefront into higher order aberrations and lower order aberrations. Now, whilst it's difficult to memorize all of them and to know the normative values, we roughly know that the average person, at least in my data set, will have higher order aberrations no more than, say, 0.2, 0.3. That's for a 6 mil pupil, and for a 4 mil pupil, that's even smaller. So they're going to be 0.3 plus minus 0.1 for a 6 mil pupil, so it's even smaller. Now this person has a higher order aberration that's measuring at 0.073. So this is a reasonably non-aberrated system. The spherical aberration here is 0.034, and we want to keep that spherical aberration down even post-surgery. 0.034 is again a very small number. The implication of that spherical aberration is its impact on the refraction. The spherical equivalent is dependent upon C4 as a parameter from here, and it's dependent upon C12 and C24. They contribute to that measurement. How much does each contribute? That's a mathematical issue, but overall, you can 6.7 times this number, this 0.034. In this particular case, it's contributing a quarter diopter. The spherical aberration is contributing quarter diopter roughly to the overall script. So it's not contributing much. So generally when you're accommodating, the C12 is not going to be the one that's going to change substantially. It's going to be the C4 that's going to change from measurement to measurement. And that contributes about 1.7 times its original value. So you can eyeball it and check where this error in the system is coming from. By just going one step behind. This is a little bit more advanced, but you can go one step behind the screen and say, where is the source of my error? Overall, that gives you the details. It also shows you the discrepancy where you're different from your subjective refraction. And you may then redirect the staff to go back and repeat the measurement and say, I like the quality of measurement, but I didn't like the accommodation aspect. Or I like the accommodation, but I need you to make the patient blink again so that I can get a better tomography to do the measurement.